the meeting. Huy Hoang Nguyen.
Thank you very much for organizing. Today I would like to present my work about the two-dimensional incompressible ideal flows around a small obstacle. This work is joined with Milton Lopez Fijo and Elena Newton-Veitch Lopez. Actually, this work is totally theoretical, not. I don't do the numerical part. Here, I will introduce the problems and some notions and the main results. After I will give some ideas about the work of the main result. Actually, the story is related to some mathematical result and about the ideal incompressible and time dependent of the flows in 2D around a small obstacle, and when we will how to say, and we will do after the obstacle will become very small. Okay, continue. The incompressible ideal fluid flows is modeled by the Euler equations. Here, U is the velocity field of the flow and P is the pressure of the flow. Actually, this flow is physically justified when the effects of the viscosity are small. Here, omega is the boundary domain and gamma is smooth boundary, and omega prime is the exterior of omega bar. Here, I will construct the U epsilon. U epsilon is the family of incompressible flows. Satisfy the Euler equation in the domain omega epsilon, with omega epsilon is omega epsilon is equal to this epsilon omega prime, and omega 0 is the initial vorticity, and omega epsilon is the vorticity associated with the flow U epsilon. Here, for the existence problem, Kikuchi already gave some many results in this paper. And our work, the purpose of the goal of our work is to identify the asymptotic behavior of the sequence U epsilon when epsilon tends to 0. Now, I construct the psi is the cutoff function which size is 0 in this ball and size is equal 1 in exterior of this ball. And T is the biholomorphic transformation from the exterior of the obstacle to the exterior of the unit disk, and mapping the boundary gamma of the omega to the unit circle. And after we construct psi epsilon. Now, I introduce the main result here. There exists a subsequence epsilon k tend to 0 and satisfied to estimates convergence here. And U and omega are the weak solution to this system.
Can I ask something about the basic setup? So is your yellow region, is that a solid body or is that a fixed body?
We choose this fixed.
It's fixed.
Yeah.
It's not moving. It's not movable. It's fixed.
No.
And as epsilon goes to 0, that body gets smaller and smaller?
What condition?
As epsilon goes to 0, that body becomes smaller and smaller?
Yeah, smaller.
Doesn't it? So what's the limit that it disappears? I was wondering where the flow comes from. Why is there any flow at all?
You're setting the initial data,
Yeah.
right?
Hmm.
And how's the initial data scaling with epsilon? Maybe you said that.
After we will do some evanescent problem, and after we tend to epsilon will tend to 0.
Well, if the body disappears, I can sort of guess what the answer is.
Yeah. Sorry.
You must scale something to keep this problem interesting as the body disappears. It's not clear to me what you actually do to get a problem that doesn't just disappear.
Well, how does the initial data scale with epsilon? Omega 0 of x.
And after I will introduce how to construct U epsilon. U epsilon depends depends on the T. After the transformation T. And we will construct the T epsilon. After we get the U epsilon depends on T epsilon.
What is epsilon? Can you define epsilon for us? What is epsilon?
Epsilon is the small number and will become smaller, and
Epsilon is the diameter of the yellow blob.
And actually in this work, we have two cases here. Yeah.
But on your previous slide, you said omega 0 depended on the curl of U epsilon, right? So there's
Yeah, omega epsilon depends on U epsilon. And omega depends on U. Here we have two cases. When the U tend to U infinity difference 0 or U tend to U infinity is 0. If U tend to U infinity difference 0, it means that the flow is past infinity. Or in this case, the flow equals at infinity. And in the case that U tend to 0 at infinity, we have this paper of Dragos and Milton Elena in 2003. Now, I will give how to show this, how to prove this theorem. First, we will do 3 steps. Here I will introduce some information on lexical potential theory about Laplacian in the exterior domain. And we will construct the conformal mappings between the omega epsilon and the exterior of the unit disk. And we can write the explicit formulas for the harmonic fields and the Biot-Savart law. After, we will formulate the flow system in the exterior of the vanishing obstacle. And we will do some a priori estimates, and after we pass to limit to get the equation limit. Here, we denote U is the exterior of the unit disk, and we can switch to the complex variable notation in this result. We can show there is a smooth by holomorphism T from the exterior of the obstacle to the exterior of the unit disk and extending smoothly from the boundary, the smooth boundary of omega to the circle. And we can write the explicit formula for T like this. Here, dt is the Jacobian matrix of the derivative of t, and we can from this formula we can show dt and dt minus 1 about it. Here, beta is the non-zero real number, and gamma is the complex number of absolute value 1. I don't give the proof here to show. First, we can pass from the exterior of the obstacle here to this domain by the IZ. After, we will use the Riemann mapping theorem from this domain plus the point 0, because from here, infinity will pass like 0 here. And with the condition R0 equals 0, we can transform from the interior of the omega, like omega 10 here, to the interior of the disk. After, we will use the squash lemma to form from this to this, and from this we use again this function, and we pass to the exterior of the disk. But here, if I don't put the gamma here, we don't need to do this step. But because it is in our proof, I need this. I need this. I need the gamma. Okay. This lemma, I will use this lemma, the last lemma, to show this result. For the harmonic vector fields, we can show there is a unit vector field V10 in C1 omega, satisfying the following problem with the condition of diversion, the curl, and this for tangents of the smooth boundary is 0, satisfy the circulation 0, and this limit is U infinity is the constant vector. U infinity constant vector, I put like alpha beta. First, I don't show is directly this problem, but I will consider another problem in an exterior of the unit disk. After I will use the methods of the pullback. I will get the pullback problem. Here, we will consider the similar problem, but for the exterior of the disk. And with this condition, with gamma equalizes. Here, beta is taken as in the lemma 1. The flow like this. Now we will write the z like a complex number instead of like this. And we define wz is the complex potential and vz is the complex velocity. And we can see vz approaches gamma at infinity. Here, phi is the velocity potential and psi is the stream function. We can check U and V satisfy the Cauchy-Riemann equations. After, with this V, we write like U, V, and we can check this V satisfy the divergence. The divergence is 0, the curl is 0. To show these conditions, we just need to show the stream function is constant. The stream function is constant. It means that this flow is tangent to the circle. Then we just show the psi is constant, and we get the result. After, we will pull back to the exterior of the obstacle from the exterior of the disk by we will denote Vt equal like this. Here, dT is the transfer of the Jacobian matrix of the biholomorphic T. And the gamma is in the lemma 1. Gamma is the complex number of absolute value 1. And satisfy the argument gamma is called the argument U infinity. And we can check all equations satisfy. Now we will consider the flow in exterior domain. The goal is in this step is to set out the precise statement of the small obstacles problem. If we consider the following initial boundary value problem with this initial boundary problem. Okay. There's some work. If omega is bounded, there's some work of Badas, Judovich, Schaffer, Walliner, and another, etc. And omega is the whole plane. We have the work of McGrath, and omega is an exterior domain. The work if U0 is sufficiently smooth, global well positioned, we have the result of Kikuchi. Now, the coupling of velocity and vorticity is given by the elliptic problem here. And we can draw the general solution of this system is given by u equal k omega plus alpha h omega plus vt for some time-dependent function alpha. And this vt in C1 is the unit solution obtained in the proposition 2 before. What is the k and h here? Here, I introduced the ring function of Laplacian here, and the k omega is the kernel of the bio-Savart and the h omega is the unique harmonic vector field and satisfy the contour integral as follows. Actually, we can write explicitly the formula k omega and h omega like this. Depends on their transformation t. Okay, here, alpha is a time-dependent function, but after we use the fact that the circulation gamma of U around boundary gamma is conserved. And then we can show alpha t does not depend on the time. To show this, we will use the stream function and the current circulation theorem. And finally, we can write the vorticity formulation of the initial boundary value problem as follows, like this, with the U equal k omega plus alpha h omega plus vt. Now, I want to consider the evanescent problem of this problem. This evanescent obstacle. Here, to formulate an objective of this part is to formulate a family of problems parameterized by the size of obstacle. And we will fix omega 0. Where is the evanescent obstacle? Evanescent obstacle is the family of domains omega prime epsilon equal this with epsilon between 0 and 0, epsilon 0. Then, after we denote the t epsilon related to t and epsilon here, and we produce the omega epsilon, we produce with the same way we will write the u epsilon, k epsilon, h epsilon, v epsilon, depends on the k, h, and v, and epsilon and t here. And I don't show here because it's complicated some process. After we get the evanescent problem, we will try to write the estimate for the velocity estimate and temporal estimate for this problem, and we will pass to the limit. There's two estimates here. After we will pass to limit, and we get is the purpose. Now, I introduce this system as it. After here, delta is the direct delta center at the origin, and we will define what is the which solution for this problem. If U and omega is the which solution, then U and omega in this space and satisfy the state function. This state functions with this test function we get inequalities, and we need to get the diversion of U 0 and the current yield equal this in the sense of distributions. Then, to show this, how to show this? Actually, it's complicated. We need to write we need to consider the estimate of this process. We need to get the velocity estimate and temporal estimate of the evanescent problem. After we will pass to limit, and we get the omega and u. After we will check omega and u justify this definition, then we can obtain u and omegas with solution to the system AZ. Okay, thank you for your attention.
Any questions?